Hello everyone, my name is Aurelien Delval. I'm a PhD student from both the Versailles University as well as Cyber. And I'm going to give you an overview of Verificarlo CI, which is a framework, as the name implies, that is based on the Verificarlo tool, and which aims at integrating numerical accuracy tests into CI workflows. So just before getting started, I wanted to mention that this work was carried out in collaboration with François Coppens and Pablo de Oliveira from the Versailles University, Eric Petit from Intel, as well as Roman Yakimchuk from the Umeå and Uppsala universities. So first, I'm going to give you a bit of context to better understand the motivation behind this work. So we start from the classic observation, I would say, that flat point accuracy has long been an important concern in numerical simulation, but that despite these facts, code developers usually neglect those floating point issues and wait before it's too late for fixing them. And when it happens, it usually takes a lot of time to fix. And well, this is time that you would have better spent solving some domain-specific issues. In parallel, we noticed the development of CI/CD tools and the lack of tools that address the issue of numerical regressions in particular. So we believe there was kind of a gap to fill here, and that's why we developed Verificarlo CI. So before getting into the CI part, it makes sense for me to give you a short introduction to the base Verificarlo tool. So it aims at tackling floating point issues, obviously. It is built over the LLVM compiler infrastructure, which is widely used in the HPC community. It has support for OpenMP, MPI, and the core idea is to use a custom LLVM compilation path, so kind of an extension to the compiler, if you prefer, to replace FP operation with calls to custom operator or backends, which are really just implementation of alternative arithmetic models. So there are quite a few in Verificarlo, but I'm only going to present two of the most important. The first one being Monte Carlo arithmetic. So it was first introduced by Todd Parker in the late 90s, and it's an example of stochastic arithmetic model. And the idea is to introduce some random noise into computation to estimate or rather modelize the effect of rounding errors. So that means that your previously non-deterministic codes will become deterministic. And what you can do is consider your results as any random variable. And so that means you can define, if you compute a sufficient number of repetitions, the empirical average mu of your results, as well as its standard deviation sigma. And from there, you can define a quantity that we call the number of significant digits, which corresponds to the equation that you see here, minus like 2 of sigma divided by mu, which is basically a signal-to-noise ratio. And intuitively, this quantity represents the number of most significant digits in your mantissa that are not going to be affected by the noise that got propagated through the succession of operations. And so this is what I represented in the first figure. So I highlighted in green the number of the significant digits, and you can see that the red digits are changing from one repetition to another. So this is really just noise that is not playing an important role in your results. And so, yeah, significant digits is the quantity that you would typically use to study codes with MCA. The second backend is VPREC for virtual precision. So this one is deterministic, and it aims at evaluating the effects of lower precision by allowing you to choose accurately how many bits you want for your exponents and mantissa. So how it's implemented in practice is that we perform the calculation in high precision. So typically quad precision has to reduce the actual physical rounding error. And then we run the results to your target precision. So once again, this is quite intuitive. I have represented it in the figure there where I have grayed out the bits that we want to disable. And obviously the typical use case for this will be to study the opportunity of using lower or mixed accuracies. So yeah, once we have said that, this is the typical Verificarlo workflow. It's split in 3 phases. So the first one is compiling your code with the extended compiler frontend to replace the floating point operation by call to your backends. And then you can run your code with all the backends that you're interested in without having to recompile your code, which can be a slight gain of time. And from that, you're going to generate a bunch of results that you can then analyze with some post-processing tools that are provided to you by Verificarlo. Some of these tools can also manage the execution of different backends for you. And Verificarlo CI is one of these post-processing tools. So it aims to be quite generic. So what it allows you to do is to define and automatically run on a CI runner some tests for numerical accuracy. And then you can also visualize these results in some HTML reports. So it integrates with the CI/CD system of both GitHub and GitLab. And so the way it's integrated in Git is around the idea of using 2 separate branches. So the first one, which we call the development branch, is the branch that you are working on with your code and that you want to track accuracy on. And the second branch, which we're going to call the CI branch, is an orphan branch that will only be used for archiving test results for one particular branch. So typically, you're only going to store some refined results using metrics such as the standard deviation of or empirical average of your results that you run in some stochastic backends, as I mentioned. But if you want to, use all the samples from all your run repetitions, you can also export the complete raw files into HDA5 formats, which you will typically store as artifacts, which are much more suited to storing a large amount of data. And so, yeah, this is basically what I explained, but summed up graphically. So this is the typical workflow that the tool will create for you if you set it up by default. But the idea is to really let user play with it to really adapt it to their needs if they want to. Okay, so the next thing we need is a way to export your test results to the tool. So we do this with what we call the probe system. So it's implemented in an API written in C, but that also has a functional interface. And what a probe really is a test variable from your code that you are going to export and identify with a test name and a variable name. And I'm going to come back in a minute to this to explain why we made this choice. Optionally, you can associate your probes with an accuracy threshold to be one in the reports when they're exceeded. And so yeah, here I've put a very simple example of a function call that would export a probe. You notice that the first argument is a structure that stores all your probes. And the backend is just a hash map. And yeah, the reason why I mentioned that probes are identified by test and variable name couple is because then when you generate your HTML report to view your results, you have access to different views. So the first one, which I would call the temporal view, just allows you to see the evolution of a single probe over time or commits. So if you have some numerical regression that you introduced, normally you should be able to see it directly. But then you have another view which allows you to really inspect a particular run or commit by grouping all your probes either by test name, variable name, etc. And the idea was to be as generic as possible, as domain agnostic as possible, and to let the user really define their own nomenclature to then get some interesting grouping in their test reports. So yeah, that's pretty much it for the tool itself. So now I'm going to cover 2 example use cases that we had. So the first one is from the NEC 5000 application, or more accurately, the Neckbone proxy application. So it's incompressible flow Navier-Stokes solver, which uses the spectral element method. By the way, this is work that was done by Roman Yakimchuk, who I mentioned at the beginning of my talk. And so the thing is that the implementation of Neckbone used some double precision, and we wanted to explore the opportunities for using single precision instead. And as I mentioned, this is typically a job for the virtual precision backend. So what we did was devising some test configuration using different number of elements. And what we did was running them through the VPREC backend. So we started with a 62-bit mantissa, which is like standard double precision. And then we progressively lowered it until things completely broke. And so, yeah, that's what we did. We looked at the residual error of the conjugate gradient solver. And when you plot the results, this is what you get. So in X, you have the X-axis, you got the precision of your mantissa. And on the y-axis, you got the different residual errors. And well, I prefer to read this one from right to left as we progressively lower the precision. And what you can see is that you have a plateau that keeps going for quite some time before things start breaking down around, like, let's say, 16 or 17 bits, which is actually good news because single precision uses 24 bits mantissa. So that means that we should be able to use some mixed precision there. This is also a claim that was experimentally confirmed by using the MCI backend. And after implementing this, we decreased the time to solution by 40%. So obviously, when you do that, you increase the risk of introducing some numerical regressions in the future. And so this is where you will typically monitor the evolution of those values with Verificarlo CI to make sure that you didn't introduce anything that could go wrong, I would say. So then the second use case is not CFD actually, it's from quantum chemistry, in particular from the QMCL library, which is a library that provides a set of kernels for quantum Monte Carlo methods. This is work that was done with François Coppens in particular. And what you are interested in here is one of those kernels, which is the Sherman-Morrison-Woodbury kernel. So what the Sherman-Morrison formula tells you is that if you have a matrix A, for which you already know the inverse, and if you want to update this matrix with a first rank update, so that is an update that can be expressed as the outer product of two vectors u and v, and then if you want to compute the inverse of the updated matrix, then you don't have to do it from scratch. You can simply use this formula, which is actually much faster to compute. And well, this is typically something in the context of quantum Monte Carlo that you will do for a few updates and to save time. So there is one issue with this formula is that the numerator, the denominator term, sorry, so the 1 plus v transpose, etc., can get close to 0. So this happens where the updated matrix is close to being singular. And this is an issue because in that case, the method is going to become numerically unstable. There is also a generalization to this formula, which is called the Sherman-Morrison formula, which you can use to apply rank k updates. So in practice, we are going to have small values of k's, like 2 or 3. And you will run into the similar issue where in the formula, you will have the inverse of at least close to singular k times k matrix. So it will also become numerically unstable. So this is a potential issue. So to fix this, we use a method which is called Slager splitting. The idea is that when you have an update that will produce a singular matrix, you split it in two. You apply the first half right now, and you keep the first half for later. So in the end, you have applied an equivalent update, but without going through an intermediate singular matrix. And so we have implemented 3 versions of the algorithm. So SM1 is the naive version, SM2 is Sherman-Morrison plus Slager, and SMWB is so Woodbury with Slager splitting. So we put this into Verificarlo CI and we run it into Monte Carlo arithmetic. So we grouped it by algorithm and we plotted the number of significant digits. And you can see that SM1, as expected, fails catastrophically in some cases, and that SM2 is much better. However, you can see that SMWB also has some issues in some cases. Which shouldn't be the case because it also uses the splitting mechanism. So we investigated the issue and we found out that it was actually a problem in our implementation. And when we fixed it, we had a look at the temporal view that I mentioned at the beginning. And here you can see that after the commit, so yeah, you have basically the time or commits and the x-axis and still the significant digits for one particular test case that I highlighted, you can see that the Sherman-Weston-Woodbury algorithm matches the behavior of SM2. So it is a nice example of how the temporal view can help you see the evolution of numerical regression over your commits. So yeah, to conclude, we believe that Verificarlo CI is a quite generic tool that could save you some time. The idea being that it's better to prevent than to fix those kind of numerical issues. We showed that it was used in the context of the CEC and TREX European projects. And if you want to go further, there is a tutorial available on GitHub, which takes you through the setup of the tool on a very simple Delval example. So that's it from me. Thank you for your attention. And if you have questions, I will be happy to take them.